Welcome to the second lecture in Unit 3. This is titled Learn the Ways of the Forces. And our famous quote is, I want to learn the ways of the Force by Luke Skywalker. And hopefully you do too. Let's see. The learning goals are that students will be able to draw the magnitude and direction of all forces acting on an object. In other words, we want you to be able to describe a free body diagram and draw a free body diagram. Finally, you should be able to relate a free body diagram to the net force and Newton's second law. So that's the term net force that we kind of excluded from the first presentation. And what we already know. We already know that forces consist of push or pulls on an object, and we also know that forces can cause an object to change motion using the equation F equals ma. Notice how we left out the net because we hadn't talked about that yet. Now, what we learned in the lab is that a force does not always cause an object to move. In fact, whenever you look at it, it's actually a combination of all the forces that are acting on an object. And the net force, or the total force, determines if an object accelerates. So multiple forces. Most objects experience more than one force. If you are not free falling to the earth plummeting in a vacuum, you experience more than one force. If you're sitting on a chair, you've got a force pulling you down, you've got a force keeping you up, otherwise you'd be falling down to the ground. Forces can be combined by vector addition, and forces must include a magnitude and direction because they are vectors. So if we were looking at the forces exerted on this top table right here, the first one is there's a force upward. I know there's a force upward because there's a force downward. Gravity's always pulling this box down, but it's not moving down or it's not accelerating down, so there's got to be a force upward. This block over the edge is pulling down, which is causing this box to be pulled to the right. Whenever the box is pulled to the right, sometimes, depending on this, the box won't move, indicating that there is a force to the left. So you've got to be able to look at all of the forces that are acting on an object. Multiple forces. So whenever you're drawing the forces that act on an object, you always start at the center. You're not going to start and have a box and have arrows pointing in towards the box. Instead, you're going to start in the center and work your way out. What we call equilibrium occurs when all of the forces cancel each other out. So for example, you have a force down, you have a force up. Those are equal, so they cancel each other out. Equilibrium results in a constant velocity or no motion. Whenever there is a net force present, it results in an acceleration. There are many different types of force that we'll go into during the course of this year. We're going to go over a couple of the main ones as we start to draw these free body diagrams. The first one that's almost always present, in fact, it will always be present when you're on Earth or on another planet. The only time that you're not going to have a gravitational force is if you're in free space, which you're not going to see in this class. So the first one we have is Fg. Fg, if you notice, all of these forces have a capital F. That stands for the force. Then they have a lower subscript, which actually is a description of the force. The subscript describes the type of force. So we have a G, which tells us that we have a gravitational force. Okay, then we have the applied force. You see an A and then an F. The applied force just means whatever you push and pull with. The third one we have is what's called the normal force. The normal force is the force that is exerted by the surface and pushes up to oppose the gravitational force. Now the key thing is that it's exerted by the surface, and therefore it's going to be perpendicular to the surface. And remember, perpendicular means at a right angle. So what that means is for a flat surface, it's going to point straight up. But when you get into something like a ramp, which we will get into later, remember it's perpendicular to the surface. So we'll get into that a little bit later. Now, you have the frictional force. The frictional force is a force that resists the motion. So if the object is moving to the right, not pushed to the right, but moving to the right, friction would act to the left. So the frictional force is something that we're going to go into more detail later. There are lots of other types of force that you can look at, including like the electric force, which would be Fe with a subscript. Okay. Free body diagrams. A free body diagram is a description of the forces based on vectors. So the first thing that you have to do is you draw a dot. You have a dot that indicates your object. I don't care if it's a car, a person, a school, whatever. The object is represented by a dot. Then what you do is you draw all of the forces that are acting on that dot. Now, the arrow length is proportional to the magnitude of the force. In other words, if I have two forces that are equal, the two arrows should be equal. Okay? If one force is smaller than the other, it should be drawn that way. Now, the second thing is you need to label all of the forces. You need to describe them as Fg, Fn, Fa, Ff, any of those things. And finally, these free body diagrams can actually be used to calculate the net force, especially if they have numbers associated with them. For example, if you had something like 10 and 12, you could look at the net force. You can say there's a 12 Newton force down and there's a 10 Newton force up. Therefore, there must be a net force or a total force acting on the object of something. So developing A1, it says draw a free body diagram for a drop of water in free fall. Now, whenever we say free fall indicates that there is no air resistance. So there is only one force that is acting on this particular drop of water, and that would be the force of gravity. So I would draw an arrow pointed down, and I would say Fg, indicating that it is due to the force of gravity. The next one says draw and label all the forces acting on a rocket accelerating upward towards the International Space Station. Now, if you were to look at this, there's a couple of different ways that you can approach this one. The first one is you have a gravitational force. That's kind of the one that you always want to start with. Now, this is kind of a tricky one because it depends on how you interpret the question. If the object is on the ground and the engines just kick on to make it accelerate, you would have a normal force pointed up. Okay? And then the engines are actually applying a force, causing it to go this way. Now, not everybody would interpret it this way. Okay? Some people would interpret it as the object or the space shuttle has already left the ground. Once the space shuttle leaves the ground, there can no longer be a normal force. If that's the case and the object is accelerating upwards, you need to make sure that you draw your vector long enough to indicate that the applied force is greater than the gravitational force. Now, as a way of checking, just to make sure that your teacher or whoever's looking at your work understands what you were trying to do, a lot of the times it's helpful to write a mathematical expression indicating what you meant. For example, here I clearly want to say that Fa is greater than Fg. So I can write Fa is greater than Fg. When you do that, it helps the person who's looking at your work correctly interpret it if they're close. For example, if my original vector was like this, and somebody looks at it and say, oh, they tried to draw them equal. Well, no, they didn't. That's not the case. You tried to say that the applied force was greater, you just didn't do a great job drawing. So if you state the mathematical principle there, it helps somebody interpret your drawing better. Next, we have the mastery level question. It says write an expression for the acceleration of a car using only the variables shown and fundamental constants. This is a tricky question. So if we were to look at it, let's see what we know. Whoops. We know that I want to look at what's called the net force. So the net force would be the applied force minus the frictional force. So I can say that the net force is equal to Fa minus Ff. And some people are saying, well, wait, what about Fn and Fg? When you're in a car, generally speaking, you're traveling along a road, you're not moving up or down, you're not accelerating through the road, and you're not flying up off the road. So the up and down forces tend to cancel each other out. So what I can say is that the net force would be Fa minus Ff. Now, if I were to look at this, people say, well, I still need to know the mass in order to be able to use the equation F equals ma. And you're right, you do. So you look at this. You have the gravitational force. Remember, the gravitational force is equal to mg. G is considered to be a fundamental constant. It is something that never changes. It's the acceleration due to gravity on Earth. So if you were to look at Fg, you can actually come up with an expression for m by taking both sides and dividing it by g. Now, some people look at this and go, oh, good, the g's cancel. No, remember, this g is not a variable. It is a subscript of f. So it's just saying the gravitational force. So I can say m is equal to Fg over g. So I have an expression for F net. I have an expression for m. You may not like it because it's all in variables, but technically at this point I can plug into my equation. I can say F equals ma, or Fa minus Ff is equal to Fg over g times a. Okay. Now I want to rearrange this equation to solve for a. Now this is a very difficult question because of the amount of variables in algebra that's involved. But if I wanted to solve for a, I need to get rid of this term. So in order to get rid of that term, I'm going to multiply both sides by g over fg. When I do that, that will cancel this term out and leave me with a on one side. On the other side, I still have my fa minus ff, but now I have times g on the top divided by fg on the bottom. So I have my expression for the acceleration of the car using nothing but variables. And you may be thinking to yourself, wow, I don't want to do that. You're right. Doing it only with algebra makes it particularly difficult. But whenever we have numbers, we're eventually going to get to the point where this becomes second nature to you. So now we want to revisit Newton's second law. We said earlier that F net is equal to ma, and we said we were going to forget the net. But now we need to take the net into consideration. Remember that the net force is the combination of all external forces that are acting on the object, and you have to combine them in the right way. So for example, if I have a box and two people are pushing in the same direction, I would have to add the two forces together, F1 plus F2. But if I have a box and I have one person pushing this way and one person opposing, I'd have F1 and F2. I'd have to say F1 minus F2. So you have to make sure that you combine the forces in the way that they're supposed to get the net force. So now you have a person that's pushing a car to a gas station. They're capable of pushing with 100 newtons of force, but he only manages to maintain constant velocity. And that's a key term, constant velocity. Use a free body diagram to explain what must be occurring. Well, if you were to look at this, does the car have weight? Well, yes, it has weight, so we can say Fg. Is the car accelerating through the road to the ground all the way to the center of the earth? No, because it has a normal force that's exerted upwards. Now, the person applies a force, which we say Fa is an applied force, and we say that's 100 newtons. But it maintains constant velocity. Remember, the term constant velocity means that there is no acceleration. If there is no acceleration, there's no net force. So that means there must be another force opposing it. Okay, we don't know what that is, but it must be 100 newtons. It could be friction. It could be another person applying a force. It could be anything else, but we don't know what it is. But we do know that there's a force opposing it of 100 newtons. So we would write our free body diagram, and we'd want to say Fa, and I would say Ff, because I'm pretty sure it's friction, that those two things are equal. And then we would say Fn equals Fg. Next, we say a 10 kilogram box is accelerated on a frictionless, okay, frictionless means no friction, surface at 2 meters per second squared. Draw a free body diagram for the box. So, the first thing I would do is I would say, all right, does the object have weight? It does because it has mass. So I would say there's a gravitational force downward. In fact, I can label that gravitational force, and I can say, remember, Fg is equal to mg, or 10 times 9.8, or 98 newtons. Okay. Secondly, the box is moving along a flat surface, so I can say the upward force is equal to the downward force, or Fn is equal to 98 newtons. Second, I know that there is a force, there's a net force because it's accelerated, and I can use the formula F equals ma. Mass of 10, acceleration of 2, means that there's a net force of 20 newtons. Generally, that means that there's a force to the right and a force to the left, and the one to the right is larger. Because it's a frictionless surface, I know that the force here is 0. There is no force. I shouldn't have even drawn it there. So that means that the force here is a force of 20 newtons, and we call that the applied force. In our final example, it says determine the acceleration of the truck based on the free body diagram below. So this is what we were talking about before, where you have all of the forces and you want to solve for the acceleration. Except this time it's a little bit easier because it has numbers. The first thing that you want to do is you want to find the net force. If you look, up cancels with down, and then left and right, if I were to subtract those two because they're in the opposite directions, I would have my net force of 80 newtons. Now I need to determine what the acceleration of this car, or excuse me, what the mass is going to be. I look at the gravitational force and I say Fg is equal to mg, and I would say 80 is equal to m times 9.8. I would divide both sides by 9.8. Your teacher may have you use 10. If you divide both sides by 9.8, now you have your mass number. Okay. For the purposes of this calculation, I'm going to go ahead and use 10 because a lot of teachers would prefer that you use 10 just to make the math a little bit easier. The acceleration due to gravity is actually 9.8, but sometimes you're rounding to 10 just to make the calculations easier. In this case, the mass is 10 kilograms. You have a net force, you have a mass, so you can use the equation F net is equal to mass times acceleration, or 80 is equal to 10a. Divide both sides by 10 and you get an acceleration of 8 meters per second squared.